Okay, so there we go. We know that the sun is doing this because of the neutrinos coming out. Okay, now we're finally done with that super technical thing. Now what we're going to talk about is we're going to talk about the layers of the sun. Okay, so what I'm going to do is I'm going to go back to my document cam. All right, here we go. And I'm going to hope that it's still working. Looks like it is. What we're going to do, and I recommend that you do this with me, is, or at least go back and do it if you view the video later, is we're going to draw a little diagram of the layers of the sun. You're going to need to know the order of the layers of the sun for the test. So what I'm going to do is I'm going to draw a big rectangle. There we go. Here's a big rectangle, all right? And this rectangle is going to represent the layers of the sun. The very center of the sun is the bottom of the rectangle, and up here is the top of the sun. Does that make sense? So we're kind of like a slice of the sun. And we just talked about the middle layer, which was the core. So I'm going to label that as the core, okay? And we're going to work our way up. Now, couple of questions. As you go away from the core, as you go towards the surface of the sun, what do we expect to happen to both the temperature and the density? What should happen to the temperature and density as you go away from the core? That's correct. They should go down. They should decrease, right? They should decrease as you go away from the core. And so that means the next region of the sun, above the core, is going to be not as hot as the core and not as dense as the core, but still very hot and very dense, okay? This particular region is the radiative zone. Radiative zone, okay. There we go. And be very, very, very careful. It's not the radioactive zone. Be very careful with that. It's the radiative zone. That means something totally different. I'll explain the name in a second. But think of it as it's like the core, but it's not quite hot enough and dense enough for fusion to be happening. Fusion only happens down here, not here, okay? Now, that said, it's still extremely hot and extremely dense, so all of the atoms here are ions, okay? They're missing which part? Which part of the atom is missing here in these ions in the radiative zone? Which part's missing? Yes. Yes. The electrons. It's missing the electrons. Now, let me bring back something from a long time ago when we were talking about how atoms absorb light, when we were talking about the fingerprints. The part of the atom, remember when I got up on the tables and I fell off of all the tables over and over again in class? I was trying to explain like atom levels. When we were talking about that, we learned that the electron is the part of the atom that absorbs light, okay? So we just made a whole ton of gamma rays down here in the core, and they're going to try to work their way up, but because this layer has no electrons attached to the atoms, that means the atoms in this area are not going to be able to absorb the light. So that means the light is free to make its way up through this region without getting absorbed, okay? But it's still extremely crowded in the radiative zone, okay? Let me give you guys a metaphor, okay? Let's say that you went to a party, okay? You went to a party, and it was not a lame party. Let's say that it was extremely lit, okay? It was just an amazing party, okay? Like it was packed way beyond the fire code for whatever building you were in, okay? And everybody's dancing, and it's just an amazing party. Everybody's dancing really energetically because the temperature's really high. This party is the radiative zone, by the way. That's the metaphor. And I was trying to get a public domain picture of a party to bring up to help illustrate this. And I thought it was funny. The very first couple of pictures that came up when I searched for a party was this. So here you go. Here's our amazing bumpin' party. It's amazing. So here you go. You're at this party right here. Imagine this was more amazing than you thought. Okay, so these people, they're all listening to dubstep or something, I don't know. And they've got their goose up here. They're just passing their goose around. And let's say that like this, that's you, okay? That's you. And you're just, yeah, okay? You're over here, yeah. And then you notice, I've got to go to the bathroom, okay? And the problem is the bathroom's way over here, all right? The bathroom's way over off this side. Are you going to be able to just rush in a perfect straight line, just shoom through this party? Are you going to be able to travel in a straight line through that party? When you're trying to get out. Let's assume that you're not a jerk, okay? Let's assume you're not a jerk. So instead, when you get up to people, what's going to happen is as soon as you get up to a person, you might accidentally bump them, but you're going to kind of go out of the way, and then you're going to turn, and you're like, oh, excuse me, and then you finally get off to the bathroom, okay? So like over here, you're stuck in the back corner, you want to get to the bathroom, you gotta before you get out, right? Lots of bobbing and weaving, exactly. So what that means is you can think of the picture we were just drawing right here. This radiative zone is the party zone, right? This is the party zone, and the light is stuck down here at the bottom of the party zone, and the bathroom's up here. It wants to go through the party. Is the light going to be able to go in a straight line through this party? No, it's not. It's going to have the same exact problem that you had going to the bathroom, right? So what it's going to do is on the way out of the core, it's going to bump off of tons of atoms on the way out, and it ends up going in a random path on its way up to the top of the party. So the light slowly works its way up through this zone. It's not able to go in a straight line. And check this out. Every time it bumps into something when it's going through the party zone, what happens to its energy? What would you expect to happen to its energy every time it bumped into something on the way out? Exactly. It loses energy. Remember, the type of light that's being made in the core is gamma rays, but we know that it's visible in UV that comes out of the sun. And it's mainly because of the radiative zone, the party zone. It bumps so many things on the way out that it loses a ton of that energy, so that by the time those photons come out of the sun at the edge of the party, they are now in the form of UV invisible light, which are much lower energy. Okay, so that's why we're not getting blasted with gamma rays all of the time. It's a good thing that this party is so lit, right? Okay? So, here we go. Here we go. Now, what's happening next? All right. The next zone is even less dense and less hot. In this zone, a lot of the atoms have some of their electrons attached to them. You start getting some regular atoms mixed in with your ions. And if some of these atoms have electrons, what can those atoms do when this light gets to them? What can the atoms in this zone, this next zone, do if they do have electrons? What can they do when the light hits them? That's right. They can absorb the light. So as soon as the light enters this next zone, it gets absorbed. So it gets absorbed at the bottom of this zone. So every time one of them comes up, they get absorbed. Now that's going to make the gas that absorbed the light hotter than everything around it. And what's going to happen to that hot gas? If that gas is hotter than all the gas around it, what does it want to do? The gas that just absorbed that light got hot. What will it want to do? What happens when you have a hot gas or liquid? It's actually taking us back to something we talked about the planets. Yes. Yes. It rises. It rises. That's exactly correct. So what's going to happen is in the party zone, the gas just jiggled around randomly. But in this region, because the gas is now picking up that light and getting hot, it's going to want to rise. So hot gas will rise. There we go. And as it gets to the top of this zone, the gas gets thinner and thinner and thinner, that it loses its light at the top of this zone, which makes that gas cool back down, and then the cold gas will sink again. So in this region, we have hot gas rising, taking light up to the top, losing its light, getting cold, and sinking right back down to pick up another shipment of light. Okay? What do we call that? What do we call hot gas rising and cold gas sinking? What's that process called? Hot gas rising and cold gas sinking. What is it called? Yes, 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 it's called convection. And so this part of the sun is called the convective zone. So this zone is not a party, okay? This zone is not a party. The core is where the light gets made. The radiative zone is the party zone that all of the light has to bump its way through on the way to try to get to the bathroom, right? And then the convective zone is like somebody kidnapped it and threw him in its trunk and drove it to the edge of the zone and then just tossed him out on the side of the road. So the convective zone is where the light gets a ride, whether it wants it or not, okay? All right. Now, yeah, sorry, things got a little dark in the convective zone, figuratively, okay? Now, here we go. At this point, remember, you guys said that the density keeps decreasing as we go up. So when we get to the top of the convective zone, the sun is so thin that the gas can no longer block the light. So as soon as the light gets here, the light just leaves and goes to space. Okay? The light of the sun leaves the sun at the top of the convective zone. And so that means when you look at the sun, what you're actually looking at, you can't see the core, you can't see the radiative zone, you can't see most of the convective zone, but because the light is leaving at the top of the convective zone, you can see the upper edge of the convective zone. So that big yellow circle that you normally think of the sun being, that's the very top of the convective zone that you're seeing. And because that's the part we see, we give that part a different name. It's technically the top of the convective zone, but we give a very, very thin layer of gas right there at the top of the convective zone the name the photosphere. Photosphere, okay? So it's called the photosphere because that's where the light leaves the sun. And remember, light is thought of as a bunch of particles called photons. So you can think of the photosphere as where the photons leave. And so again, the photosphere is the part you see when you look at the sun. Also, don't look at the sun. Looking at the photosphere can permanently damage your eyes in seconds. Okay, you could go permanently blind looking at the photosphere in seconds. Please don't look at the sun. Okay, one quick thing. If the light right here is this, if this is where the light leaves the sun, does anybody remember how long it takes that light to get from here to the Earth? How long does it take the light to get from the sun to us? How long? Yeah, just a few minutes, about 8 minutes, okay? And so the light goes a crazy, insane distance in 8 minutes. This distance between the core and the photosphere is not even a billionth of it's billions of times smaller than the distance from the surface of the sun to us. I might be exaggerating that a little bit. It's a lot smaller, okay? So what amount of time would we expect it to take the light to go from the core to the photosphere? How long does it take the light to go from the core to the photosphere? Would you expect? Seems like it would be like that, like seconds at the most, right? But it turns out that it takes light about 150,000 years to go from the core to the photosphere. 150,000 years to get from the core to the photosphere, to leave the sun. So that's a big difference. So can anybody figure out why? Why does it take a ridiculous amount of time for the light to get out of the sun? Yeah. It's the party zone. The party zone is so packed. It's so bumping that the light hits so many things on the way out that it's so crowded that it takes 150,000 years or so for that light to get out of the sun. Okay, so it's ridiculous, is what I'm getting at. Does that make sense? And then as soon as it's free, it can take just 8 minutes to go to the Earth. All right. Now, just so you know, we sometimes call the photosphere the surface of the sun, and all of this stuff underneath it is the interior or the inside of the sun. But can you walk on the photosphere? Even, like, assuming you could survive the temperatures or whatever, could you walk on the photosphere? Could you walk on it? No, you can't. Why not? Why can't you walk on the photosphere, even if you could survive the temperatures? Yeah, it's made out of gas. Every single part of the sun is made out of gas. Technically, again, a lot of it's plasma, but it's gas, right? So all of this down here is gas. and the photosphere is gas, and everything above it is gas. So us calling that the surface is kind of just a convenience for us to make it seem like something we're familiar with. But even though this stuff is considered the interior of the sun and the rest of it, photosphere on up, is considered the atmosphere of the sun, there's not really a physical difference in the type of material we're talking about that much. Okay, it's all gas.